Hello there, and welcome to session 7A of Bridgetech's online training sessions. I say 7A because this is the first of a two-part series. We're going to be looking in section 7 at OTT, but I wanted to split it up into two distinct elements. First of all, I'm going to talk in this session about OTT theory and how OTT works. There's still a bit of confusion out there about how OTT works, so I thought I'd clear up some of those. It's not an in-depth tutorial about HLS or any of the other formats, but it is about the generalities of OTT. And in 7B, I'll be looking at how our probes monitor OTT services, how we actually get the chunks, how we evaluate the chunks and the metadata, and then how we create a monitoring database. So let's look at OTT. Over the top basically just means over the top of the internet, over the top of all of the other traffic that is on the internet, and it's just a method of content delivery. So whether it's a live video stream without a beginning or an end, or something fixed length like a movie or a TV catch-up, that's delivered at least partly over the public internet. So we use various protocols, chief amongst which will be the HTTP and TCP protocols. Now, I'm not going to delve into a huge amount of detail about TCP or HTTP, but there are many resources out there on the internet. I will actually look at TCP a little bit because it's quite interesting, but these protocols are used and enable lost packets to be retransmitted if necessary. Remember, an IP packet can contain up to 7 MPEG transport stream packets, and if you lose a single IP packet, then that could have an effect on picture quality. 7 MPEG transport streams, video glitch, an audio glitch, or some table information. So cast your mind back a few years to IPTV systems. IPTV systems came to the fore probably about no longer than that, actually 18, 19 years ago. The service provider would control the network, the distribution network, so that enabled them to provision the network. They could send UDP packets across their own managed network with near certain expectation that those packets would reach the end user. They could provision the network, they could ensure that the right amount of bandwidth was available. Because remember, any of these packets dropped would cause an issue at the customer's TV set. So IPTV systems are limited by the reach of the managed network owned by the ISP or the distributors. So they can only really effectively distribute in their own managed network. And of course, if the internet could be used, then the reach could be extended across the entire world effectively. There are lots of problems, of course, inherent with using the public internet. There's a lot of competing traffic, all of the rest of the internet. We've already discussed that UDP protocol cannot guarantee reliable packet delivery because a lost packet is lost forever. UDP is often described as fire and forget. An ISP has no control over the rest of the internet, can't do anything to provision the rest of the internet. And of course, if I'm sending down a large trunk to a large city, then I may have a lot of network capacity. But as soon as I reach the edge of my network, then capacity obviously goes down, and different parts of the world, different cities, different locations have different bandwidths available because of the delivery mechanism. And security can also be a problem. Your content owners want to protect their content, and if it's available on the public internet, how do I protect it? How do I stop people intercepting packets? The internet's been around for a long while, and we've been able to send files reliably since its inception. What's the problem with live TV? Why can't we do it with live TV? And it isn't a problem if we use the same protocols for moving files. We've been able to deliver web pages, and before that, and concurrently, of course, emails for a long time. Emails don't arrive with words or letters missing. They arrive reliably. How is that achieved? What are the mechanisms that enable these files that are being transferred around the internet for years and years and years? How do they arrive reliably? Well, it's down in major part to a protocol called TCP/IP. And this provides a mechanism for tracking packets. A sender and a receiver are joined together, and they have a session is established, and packets are sent in bursts. And if a packet is not received, then it is retransmitted, and it uses a series of handshakes. Again, it's quite complex, but in essence it's quite simple. A sender sends packets and a receiver acknowledges those packets, and if an acknowledgement is not received, then those packets are resent. And it starts very slowly, and then it ramps up the speed that these packets are sent and how rapidly they're sent, and it can slow down again if necessary as network conditions change, as they always do. TCP is less efficient in its use of bandwidth. For a start, it's one sender to one recipient, so it's a point-to-point connection. UDP multicasts, of course, are one sender to multiple recipients. Much more efficient use of bandwidth. So live video is not a file. It doesn't have a beginning, or it does have a beginning, but it doesn't have an end. So we need to break up live TV into sections or chunks or segments. And then these segments, in the picture you can see they're 10-second sets, just a file with a beginning and an end. So we send that file as we would send an email or a download of a music file or any other data file. The chunks are stored at the origin server. So they can be scrambled at this point as well. So that addresses the content protection issue. And then metadata files are associated not only with the entire stream, but with every individual chunk. So the receiver knows which is the next chunk and where to find it. So this metadata are manifest files. Chunks then are usually forwarded from the origin server to a content delivery network. This could be owned by the individual company. More and more third-party companies like Amazon Web Services, Akamai, and people like that are offering content delivery networks to smaller operators, and this is becoming a more and more used option. So applications on the smart devices request the stream manifest. So the manifest tells it where the content is located and how to request it. And the stream and profile manifests, I'll talk about profiles in a minute, enable the application that's playing the video to keep track of where it is. Usually, as the display of one 10-second chunk is ongoing, then the next 10-second chunk is being downloaded in the background. So different parts of the internet have different speeds. So let's just imagine that, as the slide shows, the next door neighbour's watching at 4K, but I'm watching on my telephone. I'm not expecting a 4K picture on my small smartphone. So how does that actually work? We missed out a section at the chunking server. We've got these 10 seconds chunks of the video. So we use something called adaptive bitrate streaming. Adaptive bitrate streaming is a concept that is used in OTT delivery. So the live video goes into what is called a multi-format encoder, and it creates a series of profiles. And as you can see, we've got 5 profiles here, starting with profile 0. And that is always, profile 0 is always the highest quality. So that's your 4K Stranger Things. Out of the multi-format encoder, each of the encoder segments, if you like, is set up for a different resolution and a different bit rate. And profile 4 in this particular example is 704 and 576 standard definition. And these profiles change depending on the material, depending on how much bandwidth is available. whether something is free, for example, or it's a premium service that's paid for. All of these commercial decisions will come in, as well as the technical limitations, to determine how many profiles and what bit rates are being used. So the multi-format encoder these days is commonly associated with a chunking server. So a live video feed will go into a multi-format encoder and out will come the chunk straight to the origin server. If we look at the CDN, we can see here that we've got 4 profiles. Remember, profile 0 is always the highest quality profile, and here it's 4 megabits per second. Currently, my tablet is looking at the 2 megabit profile 1 because it will always try to get the highest quality profile that the network conditions allow. And this will continue playing for as long as network conditions prevail. Now, if the network conditions deteriorate, then the display device will drop down a profile to profile 2. And here you can see it goes down to profile 2, which is the 1 megabit profile. And this will then happen at the chunk boundaries. So it's seamless. The customers won't notice any change. They may notice a change in the quality, and if it drops down significantly and there are multiple profiles, then a drop in quality is quite obvious to see. And you've probably all seen it if you're watching Netflix or Prime. It is quite possible to see these, but it happens on the chunk boundaries, so it's not so intrusive. And there is a problem with this means that the profiles must be completely aligned, otherwise this transition will not be seamless. And that's one of the things that a probe is looking at. It's looking for this profile alignment. There are various flavors of OTT. They're all essentially the same. But they do things slightly differently, as it happens in the world. Everyone seems to think that their idea of doing something is the best idea. So we've got HLS, which stands for HTTP live streaming, HDS, which is HTTP dynamic streaming. Then we've got smooth streaming, and of course MPEG-, because MPEG came to the party rather later than everyone else. And RTMP, which has been around for a long time. It predates OTT as a concept and has been around for a long time. So HTTP live streaming, HLS, has been around for a long time. It's developed by Apple and it's part of its QuickTime. It's basically a transport stream encapsulated into this HLS format. It's very widely adopted. It has a simple DRM. The default chunk length is 10 seconds. It can be changed. It can be deployed on any standard HTTP service. It's very widely adopted because of that. HDS is Adobe's second generation streaming protocol. It's very similar to HLS in the way it's worked. It's still called Flash. It's not as widely adopted as HLS, so you don't see it quite as widespread. It provides more DRM options than HLS, but it can't be deployed on standard HTTP servers, so that's one of the limiting factors for HDS. Smooth streaming is Microsoft's proprietary format. Its chunks are generally up 2 seconds. 2-second chunks are far more easily cached, and it makes the movement up and down profiles, when we looked at adaptive bitrate streaming, it makes that movement much quicker, more dynamic. It allows for trick plays. It has very good DRM, as you might expect from Microsoft, but it can't be deployed on standard HTTP servers and is often used in Microsoft Media Room type environments. MPEG-, we said MPEG came quite late to the party, but it's the first international standard. Again, it's backed by MPEG, so it has a great deal of status, and it is used by many people. It's becoming more and more widely adopted, and it will probably become the streaming standard eventually. It's completely independent of whatever coding you tend to use. RTMP, well, that's been around for a long time, real-time messaging protocol, in fact. And it was developed originally by Macromedia and called Flash. Of course, Macromedia was acquired by Adobe, and RTMP was then adapted and became HDS. Bridgetech probes do provide RTMP validation. It's not as extensive as the monitoring for all of the other formats, but you can tell whether you have a live and active stream. So that really concludes the look at OTT theory. So now I think you're in a better position to see when I talk about profiles and manifest files and HLS and HDS next week, you'll have a little better idea of what we're talking about and why it's important for these manifest files to be monitored and how the chunks are monitored and what it means when I talk about profile alignment. So thanks very much for joining me. I hope you'll take the quiz. Just a few questions to test your knowledge. Remember, you can watch this as many times as you need. And there is a great deal more information out there on things like TCP and indeed HLS and HDS and Smooth. There is a great deal of information if you find the subject interesting and you want to delve more deeply into it. So with that, I'll bid you goodbye and look forward to talking again next week.